Hi everyone, and welcome to our second lecture on torque and moments. Today what we're going to talk about in this particular lecture is a little bit more of a nuanced understanding of some particular things in this subject area that will help make your problem solving a lot more efficient and easy. So the two topics that we're going to talk about specifically are how to deal with force components, essentially what we talked about in Unit 1, and how that relates to moments. And the second thing we're going to talk about is line of action, which, through a couple example problems, I think you'll realize is a very powerful tool in solving ENES 102 and real-world problems, specifically when it comes to moments. Let's first talk about force components and how that relates to moments. To get things started off for this particular lecture, what I want to do is actually ask you a question to start things off. So, look down at the example shown below and assume you're working around the house because there's all sorts of projects you can do. And your dad says, hey, can you tighten this bolt for me? Hands you a wrench. Now, if you've got the choices shown below, A, B, C, D, E, or F, which force would be the most effective at tightening the bolt? I'll give you a minute to think about it, and then we'll come back and answer the question. Alright, have you thought about it a little bit? If so, it's actually an interesting question to ask. And sometimes in engineering and in the real world, it's actually very effective. Instead of asking the question that you've been given, in this case, what is the best force to tighten the bolt? Let's start off by answering the opposite question, which is what is the least effective forces to turn the bolt? Because if we can answer that question, we'll be able to work backwards and answer the first question, which is to figure out what is the best force. Now, if we're asking ourselves what is the least effective force in this case, you guessed it, the answer is obviously C. If someone handed you a wrench and asked you to tighten a bolt, and you applied the force at C, chances are that person is not going to trust you to be an engineer ever. That is really, really not what you want to do. It's not tightening. After C, what are the other worst forces to apply to this bolt? Well, we can see that B, E, and D are all perpendicular and fairly far away. But the forces that are the closest are A and F. Because those two forces are extremely close and they're at an angle, we can actually see that in some ways the forces of A and F are similar to C, and that some of their components, shown here in yellow, actually are parallel through the line that passes to the bolt. As a result, those forces are not very efficient, and only a small component of the force is actually perpendicular to the bolt and turning it. So, we know that the answer is not C, it's not A, and it's not F. Knowing that moments is force times distance, which force has the greatest distance away? Well, that force is force D. Now, you'd think that the answer to this question would be D, but actually, you'd be wrong. You would have gotten tricked because the question asks you to tighten the bolt. Remember, righty-tighty, lefty-loosey. So the answer to this question is actually force E, because that will be the force that causes the bolt to rotate clockwise and actually tighten. This brings us to an important point, which is essentially that torque and moments, while it's equal to force times distance, is really force perpendicular times distance. If a force is parallel and goes through the point of rotation, like the force of the wrench through the bolt, then it's not going to turn that system. A force has to be perpendicular to the moment arm in order to get things to rotate. That's why it's really important to distinguish that the moment about a particular point caused by a force is equal only to the perpendicular component of that force times the moment arm. And we'll show this in an example next, but a quick way to illustrate this is to think about how you might open a door. Of course, I'll be happy to open the door for you. Let me get it. It must be the other way. Hold on. I guess it's locked. Alright, now let's hope that you didn't try to open a door that way. As a human being, pretty much all of us know that to open a door, we apply force at the doorknob and pull it open that way. Now why did the other forces not work? Well, because when you see the door rotate, it rotates about its hinge, right here, this pivot point. When I try and pull in the door this way, absolutely nothing happens because my force is parallel to the hinge. It doesn't work. But when I apply a perpendicular component of force to the door, about the pivot point, it actually does work. Now, one other cool thing you can see here is, as I've told you many times before, engineering design is all around us. Look where the doorknob is on this door. It's not close to the pivot point. It's actually as far away from the pivot point as is physically possible on the door itself. The reason being that the greater the distance here, the lower the force you need to apply to create the same moment necessary to cause the door to rotate about its hinge and open. There you go. Moments applied in a silly way in the real world. Alright, now that you've seen me open a door very, very poorly to hopefully illustrate the point that perpendicular force is what matters in moments, now we're going to look at an example problem and solve this to show how we can calculate the moments caused by a force that has a perpendicular and a parallel component to the point of rotation. Now let's look at how to solve this problem right here. What we can see is we've got our wrench right here. We've got two forces applied to it. Force F1 is applied some distance L1 away from the bolt, and force F2 is applied at an incline at an angle of theta, which we're given is equal to 30 degrees, some distance L2 plus L1 away from the bolt. The question that we've been asked here to solve is which of these two forces causes the greatest moment about our pivot point of the bolt over here. So how do we solve this? Recall just a second ago we learned that moments are equal to force perpendicular times distance. So we need to make sure that we understand that the perpendicular component of force is the most important when it comes to causing a moment. When we look at force F1, F1 is already perpendicular to our wrench. Therefore, it is very efficient and will cause a maximum torque. So, to figure out the moment caused by F1, we simply can multiply the value of F1, because it is perpendicular already, by the distance away from the pivot point, which in this case is L1. As a result, we can plug in our numbers and see what we get. So we're going to have 15 newtons times L1, which is 0.1 meters. This is going to get us a value of 1.5 Newton meters. Now we can look at the force F2 and see what moment that causes. So the moment of F2 is going to be the perpendicular component of F2, which if we see, F2 has two components actually. It has a component that's going this way, and it also has a component going this way. Now if you look, this component right here, more or less would actually go through the bolt. So that component doesn't matter in our calculation here. The component that does matter is this one. And something just to kind of clarify with vectors is to notice that I've drawn this component right here, but it's applied off in space. Realistically, in this problem, we want to be applying the force in our y direction. If we use this xy axis, we want to use this component right here. So you want to make sure that the arrows of the forces you're actually applying always touch the arrow of the original. But you can see that this arrow and this arrow here are going to be equivalent. So how do we solve for this component right here, F2y? Well, going back to what we did in the first unit, we can see that F2y is going to be equal to F2 times the sine of theta. Why is this the case? Just to review really fast, remember that the sine of theta is the opposite side, which in this case is F2y, divided by the hypotenuse, which is F2. Therefore, F2y is equal to F2 sine theta, which is, if F2 is 10, and theta is 30, the sine of 30 is 1/2. So we get 10 times 1/2. This gets us a value of 5 newtons. Okay, now what we need to do is, now that we've found the perpendicular component of F2, so our 5 newtons is effectively F2 perpendicular, we can multiply that by the distance of L1 plus L2. So we get a value of 5 newtons multiplied by 0.2. And the answer that we get for this particular question now is that the moment caused by F2 is going to be equal to 1 Newton meter. So what does this answer mean? Well, if you look, the force that's closer actually provides a greater moment about the pivot point than the force that's farther away. And the reason is that even though you're farther away, which should make your life easier, you've inclined the force here, which actually makes it less efficient. And because it's less efficient, we're not applying all of it, we're only actually applying half of the force in a perpendicular sense. It actually does not result in having a greater moment. So, in moments, two things are important. The distance away, which the greater the distance, the greater the moment's going to be, and the efficiency of your force, meaning how much of your force is perpendicular to the moment arm in question. Okay, hopefully that last example helped to illustrate how you use force components along with moments. And a quick note here, a lot of times in textbooks you'll see that moments will always be given as torque is equal to force sine theta or sine of phi in this particular case. But be careful, that's not always the case. Look at this particular example right here. In this particular case with the wrench, the torque is not F sine theta, it's actually F cosine theta. So just always make sure that you don't use equations from the book. You use your good old noggin here to make sure that you're doing the right thing at the right time. Now let's talk about line of action and how this tool and kind of theory really helps you solve moment problems a lot more efficiently. Let's start off with a quick demo. So, what is line of action really all about? Let me show you this concept with a quick little demonstration using this little metal cylinder and this handy dandy string that I've tied to it. Now the point of line of action is that you can move a force along the line that it's applied to, and the physics and what's felt by the system will remain the same. Let me illustrate this. If I take this mass and hang it from the string and hold it in my hand, what my hand feels right now is I feel the weight of this cylinder pulling straight down. If I let out a little bit more string, I've now changed technically the spot where the force is applied. It's applied lower than it was before, but it's still applied along the same line. So my hand and arm still feel the exact same force of the weight pulling down right here. And I could extend this weight even farther down so you can't even see it on the camera anymore, but yet I can still feel exactly the same thing. So what line of action is trying to essentially accomplish is it's essentially trying to teach you that you can move that force along a given line and the physics of the problem will remain the same. So as you just saw in that demo, no matter what, as long as you apply a force along a particular line, the outcome, at least in terms of physics, is going to be the same. So as long as you apply the force along the same line of action, you don't change the physics of the problem. The example I kind of showed you is very much similar to this case right here with a wagon. When you pull on the wagon, if you pulled at the top of the string, or whether you pulled closer towards the wagon, at the end of the day, the wagon is still going to behave the same. It's going to be pulled to the left, no matter what. So that's really what line of action is all about, and that's what's shown here with this blue dotted line. So ultimately, one other way to think about this is to consider a block. If I push the front of the block with force F1, that's going to be the same as if I pulled the block with force F1 at the same location on the block. I can move a force along its line of action, in this case, from the left side of the block to the right side, and the outcome and the forces felt by the system is going to be the same. That's what line of action is all about. This leads us to a very important concept related to moments, and that it's important to distinguish between the two ways that we now have to solve for moments. One is what we've already done, which is that moments are force perpendicular times distance, and the other, which we're going to talk about right now, is what's called the line of action methodology, where we take the force, we slide it along this line of action, and we find not a perpendicular component of force, but rather a perpendicular component of distance. And I'm going to give you an illustration of how we do that by showing you this example problem right here. What we're going to analyze is this particular problem, which is the classic ladder leaning against a wall. And I'm going to show you how to solve for the moments about point A caused by the weight of the ladder using both methodologies that we now have. And hopefully this example will illustrate the difference between the two methods and show you how one might be more efficient and useful in the future when solving problems. Let's look and see how line of action can be applied to this particular problem here, which is your classic ladder problem. The question that we've been asked to solve for, essentially, is what component of the weight is going to cause a moment about the point down here, and what is that going to be equal to? What we can see with our ladder is that it stands 4 meters tall and 3 meters wide, meaning that the overall length of the ladder, shown here in pink, is 5 meters. And just in case you didn't know, I wrote ladder here at the very top. That way it's ultra clear it's a ladder. So there's two ways to solve for the moment caused by gravity about this point down here, which we'll call point A. Gravity of the ladder is going to act through the center of mass, which is right here in the middle of the ladder. And we'll draw gravity pointing down right here. We'll just call that weight. Okay? So if that's the case, we can see right here that we've got some angle theta, which isn't given to us, but we could define that if we so chose. And we know that there's two ways to solve for moments. We know that now moments are equal to force perpendicular times distance, or they are equal to force times perpendicular distance. The whole point of this example problem is to showcase how you do this in a real problem and how you use line of action to your benefit. So how does this work? Let's look at the first way that you already know, which is to find the perpendicular component of the force times the distance. Well, if we look here, the weight is not perpendicular to the ladder. We would have to break that weight up into its constituent forces, which would be the following. We'd have a component that's perpendicular to the ladder, and we'd have a component that's parallel to the ladder. Now, the component we care about in this question here is obviously the component that's perpendicular. Now, the way that we do that is we understand that the theta here is going to be equal to the theta here. And I'll explain this further on at a future point in actually the next unit, but just take this for granted right now. So if we know that this is theta here, then this component right here is going to be equal to W times the cosine of theta. Okay? So the moment caused by the weight of our ladder about point A is going to be equal to W cosine theta times the distance. Well, what is the distance? Because this is acting in the center of the ladder, the distance from this point to our pivot point down here is going to be 5 over 2, or 1/2 of that distance. So if we look at cosine of theta, again, we have essentially similar triangles down here. So we can draw a little triangle. I guess I'll just do it right here so it's more clear to see. Here's our theta, and we know that our ladder is 4 tall by 3 wide by 5 long. So the cosine of theta is the adjacent over the hypotenuse. So this equation here becomes W times 3 over 5 times 5 over 2. Something you can see that happens is that our 5's cancel out because you have one on the top and one on the bottom. Therefore they get gone, and our MA, our Ma, is going to be equal to W times 3 over 2. Cool. How do we do the second way? So let's draw ourselves a nice little arrow here. Separate it out. And let's look at how we solve for the moments of the weight component about point A using line of action. So let's just make that really clear. This is our line of action method right here. Line of action. How do we do it? So, we keep the force the same as it is, and we move it along its so-called line of action until it reaches a point when a line from the tail of that vector to the point of rotation is perpendicular. So first step is draw a line through our force. This is our line of action. So we draw that here in red, in this dotted line. We draw this. Now our task is to move this force along this line to a point where it becomes perpendicular to the pivot point, which I'll outline over here. Now, when is this going to happen? It's going to happen when we move our force vector down here. So we take this force and we go, drag it down there, and we redraw W. Because now what you can see is that a line drawn from the tail of that vector to our pivot point forms a 90-degree angle. This is what line of action is all about. So, now in our calculation, the moment is going to be equal to the weight, because we've kept it the same. Now what we need to solve for is this. Distance perpendicular. Well, the distance perpendicular is this distance right here. And if you remember back to your geometry lessons from way back in the day, you would know that if you took a line from the middle of a triangle, dropped it down, it would bisect this side. So this distance right here is actually going to be equal to 3 halves meters. So when we plug that back in over here, our distance perpendicular is going to be 3 over 2. So, what can you see about our final answers? If you check it out, the answer that we got using the first methodology tells us that the moment caused by the weight about the point A of the ladder is W times 3 over 2. The moment caused by the weight of the ladder using line of action to solve is also W times 3 over 2. It's the same answer, right? So what this shows you, I mean, look at all the work we had to do over here, and then look at the work that we had to do here. There's no mathematical work here. All of our work in the geometry and trig was done simply by sliding that force along the line of action. So in some instances, this method is going to be extremely more efficient at calculating the moment of a force. And I'll show you a few more examples as we move forward that illustrate this concept even further. But do be wary that it's not always better to use line of action. Sometimes you are going to want to use the first method that we've talked about. So pay attention and make sure that you're always choosing the most efficient methodology to solve for your moments. Now that I've shown you that example with the ladder, it's very important, as I was saying, to know when to use the line of action methodology, because it's not always the best. Here's a great example of when you should use it. When you have a force that's already like in the XY plane, but the moment arm is not, it's very useful to use line of action. Here's a perfect example that illustrates that. What we have right here is a question that's asking us to solve for the moment caused by force F1 about the pivot point of the bottom of the stressor, point A. So let's show you what it would happen if you didn't use line of action. What you would have to do is you'd have to find the distance L3, because that's the true moment arm between your force F1 and point A. So you'd have to solve for the length L3 using Pythagorean theorem, which you could probably do, you're all pretty smart, and then you'd have to draw it. But when you look more closely now, force F1 is not perpendicular, so you'd have to draw perpendicular and parallel components of force F1. Now, if you're like me, you're looking at this system right now and you're scratching your head. How do you do this? You now have to actually figure out theta. So after a little bit of tricky trig and geometry and whatnot, you can figure out theta and figure out that the tangential component of F1 is actually F1 times the sine of theta. So once you do that, then your force becomes F1 sine theta times the moment arm L3. And that would be the application of the force perpendicular, F1 sine theta, times the moment arm, L3. That's a lot of work. That's 5 steps. And ultimately, you just get a very simple, straightforward 3-part equation, pretty much. And if we plug in our numbers, if the F1 was 10 pounds, L1 was 3, and L2 was 4, we would get a value of 10 times 4/5 times 5, which, as you can see, would be 10 pounds times 4 feet, 40 pound-foot of moment. Let's look at how we would do this now in a much easier way with line of action. So this example is perfect to illustrate how easy line of action can be. Everything we just did before, those 5 steps, all that math, which we hate math, can be done by doing one simple thing. If you take your force and you slide it along its line of action at the top of the dresser, you can now find that F1 is perpendicular, shown by the dotted blue line, to point A. Your moment then becomes F1 times L2, which F1 was 10 and L2 was 4. So in one single step, you did everything you just did in the last part. While both will get you the same answer, when you have an exam and the time is ticking, it's going to be very important for you to know when to use one methodology over the other so that you're efficient and can get to the answer as quickly as possible. Now here's an example of when you would not want to use line of action because it's not the holy grail. Let's say you were looking at the solar eclipse, which I'm pretty sure you're supposed to do with a giant telescope and look at the moon passing in front of the sun directly. That's supposed to be the best part of it. I'm just kidding, don't do that, that'll make you go blind. But if you were looking here, we can see that F1 is inclined at some angle. We're given a theta. And the point we're trying to determine the pivot point about is the point of the telescope that moves this way, which is point A. So if we were trying to do this with line of action, we would have to draw this line right here. And we would have to move L1 along this line until that force became perpendicular to a line from point A drawn out to that point in space. So we could do that easily enough, but then the question becomes, how do we solve for the perpendicular distance? Because that's going to be this random distance in space. The truth of the matter is, you can't. It's going to be really, really freaking hard to do it. What you should just do in this particular problem here is take the perpendicular component of the force, F1, which is going to be F1 cosine of theta, and multiply that by the distance, L1. So as you can see, line of action isn't always the best solution. Hopefully these examples help to illustrate that point and show you it is really important to figure out when to use one method over the other. Well, there you have it. That's the end of this lecture, and what we're going to be doing in the next unit is talking more about free body diagrams and how to solve for systems using both the things you learned in the force components lecture as well as the moments lecture to determine whether a static body is in equilibrium. And that's what we'll do next time. See you then. It doesn't matter whether I lower the string down here. Whoops, I just broke the string.